back to maths. I'm sure you're excited starting year 13. Hopefully all the lessons won't be me online, but it's me for now online. And we're going to do a new exciting topic of complex numbers. Sure you remember them from last year, but today's lesson will be partly recapping. So it should be helping you for this test coming up, the AS revision, as well as maybe picking up one or two new things. We'll see. Right, so to start us off, there's 3 questions here that you should be able to answer from AS Maths. So have a pause. First one, you could use your calculator, or you could use times top and bottom by the conjugate of 6 plus 8i, and then it should work. The second one, solve that. You can use quadratic formula and solve it. Or you could do it on your calculator, but that would be cheating because it says without calculator. And the third one to solve, in other words, find z, so you've got to square root 24 plus 10i. Do you remember what to do? If you don't, here's a little clue. Change z to a plus ib, and then have a plus ib all squared on the left hand side, and then square that out, and then compare it with the 24 and the 10i. There's your clue. Right, so pause the video now and have a whirl before the answers pop up. So hopefully pause. Okay, now you've had a go, here come the answers. Oops, not in any particular order. There's number 2. I use quadratic formula. Number 1's coming up. Say times top and bottom by the conjugate. And out came that answer there. And the third one, as you recall, I said put a plus ib, square it all, expand, compare imaginary and real, and it got down to b was, well, you had a quartic, didn't you, here? Solve it on your calculator, get b as plus and minus 1. You might get a complex answer as well, but you just ignore that because a and b have to be real numbers. Anyway, so then you get b is 1 or b is minus 1. It comes out 5 and minus 5 for the a. So those are the 2 complex numbers for z. Super, hope you got those right. And if you don't, pause this again and have a good stare and see where it is that you went wrong. Otherwise, we're moving on. Ooh, remember this little song from last year? We did have it about the modulus and argument of complex numbers. If you've forgotten what those are, here we go. The modulus means length or magnitude. Complex numbers, if you ask for the modulus of this, you square the a and square the b, and then press the square root key to find the positive length from 0 to z. So what it's actually finding is the length of that line from the origin to the complex number, using a bit of Pythagoras. Argument is the angle. So the angle is known as the argument. It's measured from the positive x to the z. To work it out, we invert the tangent of b over a and take from Python quadrants 2 or 3. So it's always measured from the positive x-axis. So we're talking that angle there. Or, if I get my little pen, always measured from the positive x-axis. So, too much clutter on this table. We're talking always measured from the positive x to the z. So we're looking on this one for this angle. For this one, positive x to the z, so that's that angle. This one I've hidden here is positive, there's the positive x to the z, so it'd be an obtuse angle. And the one I'm covering up from the positive x to the z must be another obtuse angle. So it's a bit of trigonometry. And we're using tan, opposite over adjacent. There we go. Right, so can you do these? Or maybe we should have a quick sing. I'll just sing it through once. I'm sorry I haven't got the music because it doesn't work on the video. But here we go. So it's a bit of happy and you know it. Do you want to have a little sing? Here we go. The modulus means length or magnitude. For complex numbers, square A and square the B. Then add them both together and press the square root key to find the positive length from 0 to Z. The angle is known as the argument. It's measured from positive x to the z. To work this out, we invert the tangent of b over a and take from pi if in quadrants 2 or 3. There we go. If it's in quadrants 2 or 3. Here's one it's in quadrant 3. When you do this, you get the acute angle, but you want the obtuse one. And that one I'm hiding under me is probably another one where you take it away. So let's have a go. On your whiteboard, on the walls at home, or wherever your parents allow, tables, or maybe even on a piece of paper. Find in third form just the modulus of that one. So a bit of Pythagoras. Have a go. Pause the video. Answer coming up. Ta-da! 2 root 3 root 2. Second question, do the same here. Leave it in third form and find the length of this one, or the modulus of this one. Answer coming up. 2 root 7. And now we're on to, in radians, find the argument of this. So decide first. You can see that complex number will be in which quadrant, do you think? It's in the first. So we're after that angle. There. Can you use trig to get that? Tangent of b over a. Off you go. Right, you should have got, if you're doing it in degrees, it'll come out to 60. And remember to change radians, degrees to radians. If you do it in your head, it's just whatever you get. So 60 over 180. Stick it over 180 and stick a pi next to it, and that gives you the third pi. Keep everything nice and you don't get nasty decimals on some calculators. Right, here's another one. So if you want to write it in degrees and turn it round, but which quadrant is it in first? Ooh, is it going to be an obtuse angle or an acute you're after? Remember, measure from the positive x to the line. Have a go. Right, maybe you've come up with this. So the angle we're after is that one from the positive x to the z. So when you calculate minus b, sorry, the tangent of b over a, keep it all positive in your calculator. Don't put any negatives in, or it'll give you stupid answers. So if you just do the shift down ones of the positives of those two, it gives you 45 degrees. So that means that theta must be 135 degrees. And you change that into radians, 135 over 180. Stick a pi next to it, and that on your calculator cancels down to 3 over 4. Now here's another. I'll shut up and let you have a go at that one. Answer I'm hiding, aren't I? Naughty me. Minus 1.99 radians it should have come out as. minus 1.99 radians. It's negative because it's under the x-axis. Positive over the x-axis, negative under. Right, well, hope that brought some memories back from AS Further Maths Complex Numbers. So today we're doing more recalling perhaps of some of the work we've done at AS Complex Numbers, including finding modulus and argument. We've got to understand the geometric properties of multiplying by a complex number. We've got to be able to convert Cartesian complex numbers to polar form, and to be able to multiply and add complex numbers in polar form. I think we did this last year, pretty sure we did, but just to recap, so good for the test coming up. Z is x plus I, y is called Cartesian, and the polar form is that one where it says z equals r cos theta plus I sin theta. Right, what have we got here then? A bit of geometric properties. Alright, so it says, what is the modulus and argument of z equals I? And what effects does multiplying I have? Right, so the modulus of I, so if we were just to do, it's a bit silly as this one, isn't it? It's got no real, so it's just the square root of 0 plus 1i. And if we square root that, obviously we get 1. And the argument, tan to the minus 1 of b over a, if I went stupidly like that, that would be 1 over nothing. Oh dear, you'd be getting infinity. Why is that? Because basically, if you were to plot that, if you plot I on an Argand diagram, it'd be there, wouldn't it? So the angle it's making with the positive x is 90 degrees. So that's a bit strange, isn't it? So it's given on the graph where it's infinity, and if you draw the tan graph, it's infinity at 90 degrees. So that is in fact 90 degrees. Right, work out, oh, 90 degrees, what's that, pi by 2 if we're talking radians. Right, work out 2, that one times that. Oh, that's a tricky one, isn't it? So if we do that, what do we get? Well, it's not that tricky, is it? 2i minus 2. Woohoo! Right. So first of all, we've plotted this first one, 2 plus 2i. That's that one. That's been plotted for me. I've just found this, and this one, minus 2 up 2i is there. So I've just plotted that new one there. So what has timesing by I done to that stick? Can you see? It has. What's that angle there, do you think? Ooh. And modulus 1. So it hasn't, if you worked it out already. Multiplying I has transformed Z by an, should be an or a rotation anti-clockwise of pi by 2 or 90 degrees, and in fact, and no enlargement. Actually, enlargement of the modulus, which is 1. Anyway, so if you want to try that again, I'll change my pen. If you were to rotate this thing by I, what would we get? We get minus 2i minus 2. Wonder why we're doing that. Well, just to show you again, you would have had down here minus 2, oh no, minus 2, oh, 2i. Oh, that's that one, isn't it? So we're just basically rotating our answer. We're rotating our answer around again. So you get minus 2 minus 2. I see down here. Ooh. So as you can see, my dodgy drawing, that line has been rotated anti-clockwise another 90, and it's still not had any enlargement. Oh, yeah, pick one blue. So if you were to work out timesing by 2i, 2 times 2 is 4. I'll put impression there. I did that without a calculator. And then minus 4. So if we were to times this thing by 2i, this is what we get. We get minus 4 and up 4 on there. So you get who needs Desmos when we've got my drawings? So you can still see it changed this. Start with this one. It rotated it around 90 degrees, but it's also enlarged it. It's twice as long. So multiplying by 2 or transferred by an, like that. Oh, yeah, a rotation anti-clockwise of 90 degrees, up by 2, and an enlargement scale factor 2, which is the same as the modulus. So summary in here, we're multiplying a point by a complex number z, we rotate the point anti-clockwise by the arc of z about the origin and enlarge it by its distance from the origin by a scale factor which is equal to the mod of z. Well, well, well. Who text me? No. I meant to say. I went to say, was that exciting or did we know that anyway? Let's move on. Right, modulus and argument form. You can express a complex number in polar form or shorthand r theta, where r is the modulus, length of complex number with that formula, and theta is the angle made with the x-axis such that theta is between pi and minus pi, not equal to minus pi. Got the inequality. And theta is called the principal argument as long as you give it in that range. That's the one they usually ask for. There we go. So using basic trig ratios, not rotation, ratios here. Now cos theta is, what is it? Something over hypotenuse, adjacent over hypotenuse. So x in this case over r. So if we were to just rearrange that, we get x equals r cos theta. And sine theta, if you remember from your trig ratios, is opposite over hypotenuse. So y over r. So what we get there, if we do a little rearranging, is r sine theta. Hence z, which we know is there's z, so it's x plus iy becomes, just check before I press this and it all disappears. So that will become, I have to squash it on, I've not got me in the way, x, which we're calling r cos theta plus I, and we place the y now, r sine theta, and then we usually just take out the r, so we call it r cos bracket theta plus I sine theta. And there we are. Note that the length r is given as a positive number. Even if it's down here, it's still a positive, or there it's positive number. It's a length. Right, on the polar coordinate graph, you can do this on your sheet, mark on the following points. So I'll just give you a chance to do that. Remember the R's, the rotating round, the angle, start again. The 5 is the modulus, and the pi over 6 is the angle, the argument. So can you plot that on this fancy graph paper, polar coordinate paper? And the man that invented this or made it up was called, here we go, Gregorio Fontana. I think he was Italian. There he is. Not much hair. I'm sure he's a very nice man. He lived in the 1735 to 1803. So he did quite well with his complex numbers, didn't he? That era, what did he live? Can we work that out? About 68 years. I'm not sure if that's good for those days. Anyway, have a go at that before I do. Right, I'll do it tomorrow. Right, it's the first one. 5 along, pi by 6. See if you agree with me. 1 along, pi. Hope I don't get these wrong. 4 along, minus pi by 3. I'll be down there then. And then D, 3 along, pi by 4. Pi by 4, pi by 4 will be there. And 4 along the minus 2/3, leave there. Let me just get off. 1, 2, there's 1/3, 2/3, yeah, it's there, isn't it? Hope you agree with me and I haven't done anything wrong. Don't think I have. So check where you put your crosses or dots and let's move on. Right, express these in polar form. So before you grab your calculator and just do it using that, let's have a go if we were to do it by hand and think with brains. So we've done a bit of this anyway. So if we were to plot on the diagram 1 plus 2i, that would be up there, wouldn't it? That's the angle we're after. So with a bit of Pythagoras, we know it's 1 squared plus 2 squared and square root, which is root 5. And we know that the theta is tan to the minus 1 of b over a, putting in all the positives, 2 over 1. And that comes out at, let's have a note, or should we cheat? If we're in radians, 1.11c. And so our answer to z is root 5 bracket cos 1.11 radians plus I sine 1.11 radians. There, or shorthand, if we couldn't bother writing all that, it's just root 5 comma 1.11 radians. Question, minus 1 minus I. So on the diagram, -1 minus I is a dot there. So it's an obtuse angle this time, measured from the positive x to the d. Right, so the square rooting is just the same, isn't it? 1 squared plus 1 squared is √2. If I call it alpha first, alpha would be tan to the minus 1 of b over a, keeping everything positive, 1 over 1. That comes out at 45 degrees, or pi by 4. So that means theta will be negative 3 pi by 4, because that's pi by 4 there. That's your alpha. That's alpha there. Is that messy? And so theta is 3 pi by 4, but it's negative because it's underneath. So our answer to all that lot would be √2. I'm going to fit this on. Cos of minus 3 pi by 4 plus I sine minus 3 pi by 4. You can't see the plus. Or shorthand, because you can't write all in. √2 comma minus 3 pi by 4. Now remember, you can also do this on the fancy machine, if I remember, because I'd rather do it by hand. It's under, yeah, press option, complex. So let's start that again. You're in your run mode, press option, OPTN button, then F3 is complex, and then if you press your F6, you get this real to, not real, you get R and theta and A plus IB. So if we were to put in, for instance, 1 plus 2 shift and 0 to get the I, and then if I was to press F3, the R theta button, and press equals, it comes up with √5 and 63.43 degrees, because I'm in radians. But if I change shift menu into, no I don't, I've made a mess of that, exit, get in. If I change that into, I should do shift setup, shift menu, and I change it in the angle into radians rather than degrees, and I do that again, yes, I get √5 on 1.107. Oh look, see, I'm not cheating. Don't know if you can see that or focus on that at all. Never mind. Right, on we move. If I can. Oh, some more for you to do. Write the polar form of that one. Have a go. And up comes the answer. You can see that. It says pi by 3 and plus I sine pi by 3. Here's another. Windy today. And if you're wondering where Squirrel is, I'm sat on her. I'm better out to show you. Oh, she's here. Come on, Squirrel, say hello to the computer. There she is. She's been sat on. Oh, girl. Enjoys a bit of complex numbers. Alright. And there we go. Did you get that? So the bit I'm hiding is the I sine bracket minus 3 pi by 4. Okay. Oh, and another. Here comes the answer. So cos minus 1.15 and plus I sine minus 1.15. Hope you manage those. It's negative because it's under the x-axis. Okay, example 3. Express the following in the terms x plus iy, where x and y belong to the reals. Leave your answer in exact form. Right. Well, best job here is to use your calculator, isn't it, really? Just plug it in the machine. Or you could do modulus is 3, argument is 2/3, and use your calculator by pressing A plus IB, but really it's just easier just to type the thing in. Or if you just put in your calculator, you won't take it in steps, you can find out what cos of 2 pi by 3 is, and you should find out that that works out to be a half minus a half. And the other one, root 3 over 2. And when we multiply that through, that gives us minus 3 over 2 plus 3 root 3 over 2i. But as I say, you can put this in as you could put 3, and then you have to put on your calculator. It's got a funny little button. You see. Oh gosh, got such rubbish on. You have to press 3, and then the angle is on the x theta t button, so you have to press shift x theta t, and then get that arrow, and then the 2 pi by 3. And then you have to press option, complex, F6, and then the A plus IB button, and then it should give you that. And your calculator's pretty good, and it leaves it in like some standard form. Anyway, I'll try and get this up, and I never get it up. So great, right. Next one then. Express the following in x plus iy, leave an exact form. You just plug it in again, yeah, but if you wanted to, first of all, write what's wrong with that, and it's not really in polar form, not that it matters when you're in your machine anyway, but why is it not polar form? Yeah, because it needs a plus. So what that is, if we had to write in polar form too before we did it, which we don't, but if we did, we'd have to write it as minus pi by 6 plus I sine minus pi by 6. Those two are equivalent. And then put that in the calculator, and you'll find it gives you, take it in steps if you must, root 3 over 2, I'm sure you won't know, minus I over 2, which ends up being just root 3 minus I. That's pretty easy. Example 4, express these rules in polar form. Right. Okay, what's wrong with the first one? Yeah, you've got it. The sine and the cos are the wrong way around, aren't they? So you can mess about with this if you know the difference between cos and sine, about cos being 90 minus sine or something. Or you can do this by just turning them to Cartesian first and then back again. That's probably the safest way. If you were to do that, you would get 2 bracket root 3 over 2 plus I over 2 or if you've done it in machine, you'd be straight to root 3 plus I, and then change that back into polar. So you could put root 3 plus I, then put that R theta button, and it'll send you back to polar. Or if you wanted to do it all by hand, you'd be drawing out where is root 3 along, 1 up. It's there. We're after that angle theta there. So if we remember all the rules, the modulus, which we call R, is modular complex number will be 3 plus 1, which is 2, and theta equals tan to the minus 1 of b over a. It's a well-known one as well, pi by 6. So you've got your polar form Oops. There's lots of little ways to do that. Well, there it is. Right, the second one, that one just has the minus in it, doesn't it? So to write it in polar form, all we have to do is pull your minus through. There's not really a lot else to do. I'm not going to convert that one. That one's just 2 lots of cos to get it both the same, because if you remember, cos is an even function. So actually cos of minus pi by 6 is the same as cos of pi by 6. And sine is an odd function. So the minus of it is the same as the negative of the positive, if that makes sense. I'll write that down. That basically, I'm saying that sine negative theta is in fact the same as negative sine theta. That's what we're calling an odd function. And cos of minus theta is the same as actually as cos of theta. If you try putting numbers in, you'll find that works. You may already know that. Okay. Have we any more? Yes is the answer. You should remember this from AS as well. Multiplying polar form. We can multiply polar form a lot quicker, because if you remember the rules of what was happening when we talked about the geometry, it enlarges by the size of the magnitude, and it rotates anti-clockwise by the angle. Well, what that means in terms of polar form is that we times the moduluses and we add the arguments. So if we had to multiply these two rather exciting complex numbers, they both to me look to be in polar form, so we're all good to go. So we just do 4 times 3, which is 12, and we add 2 fractions, so that one and that one. So 8 plus 5 is 13. However, our angle should be in, I'll call it now, what the bastard thing, principal argument. So it's out of principal argument because it's 13 pi over 12, and we shouldn't have that. So what we have to do to get anything in that form is take away 2 pi from it, because if you think of plotting this angle, it's just over pi, so it's actually down here. That's what 13 12 actually looks like. Now to get that, we have to read it underneath, don't we? So we need to know what is this angle under here. So actually the easiest way to do it is just taking away 2 pi from your answer. So if we were to do 13 pi by 12, take 2 pi, what we end up with is in fact minus this bit. So that would be minus 11 pi over 12. Which is what we want as our answer. So it's the same, still talking about the same point, aren't we? You have to get it in the range. So to get it in the range, keep taking 2 pi away from your fraction until it becomes in the range. So our final answer will be 12 cos minus 11 pi over 12 plus I sine minus 11 pi over 12. If you like, put brackets around there. Well, that makes it really messy. Scruffy answer, but never mind. There we go. Right. Next bit. Or is there any more? So on your whiteboards, have a go at multiplying those two and see if there's a funny little trick to it. But be careful, not in polar form, one of those two before you start. Get it in polar form first. Have a go. Okay, here's the answer. I've done it in polar form there, and then I've even changed it into x plus iy form because that's what it says over there. So it didn't really ask us to polar form, but I've done it in polar form and then put it in the x plus iy form before. Not sure if I remember to do that with the last question. Sorry if I didn't. If it said put it in the form x plus iy. Just a matter of putting it in your calculator and writing down what it says. All right, last bit. I'm pretty sure it's the last bit. It's dividing them. So dividing them is opposite of multiplying. So the geometry is actually what happens to it. We are something by the moduli, so shrinking by a scale factor of the mod. And we rotate not anti-clockwise, but clockwise. So write that in. Get on the line. So we are so shrinking by a scale factor of, I don't know how to write that down, I should leave that blank a minute. So basically what we're doing, you divide the moduli. I don't know if that's going to pop up actually. There it is, yeah. We divide the moduli, so it's root 2 over 2, and we subtract the angles. So we've got both in the right form, yeah. So 1/12 and that'll be 10/12, won't it? So that's cos of 10 take, oh yeah, 10 take 1. Can I do that? 9/12, 9/12 is 3 over 4. Plus I sine. Oh, but it's that take that, isn't it? So it's minus. And that's in our polar form. So if it said polar form, we leave it there. But then it says x plus iy, just so stick it in the machine. And finally, you can mess about with that, but that comes out at minus a half. Minus a half I. I think I want to write here. Here we the mod. I think I put mod there. It's shrinking by the mod. Don't really like that. We are. I'm not going to leave it blank, so I don't like it. But basically, you're dividing by the scale factor of 2, and you are rotating it clockwise rather than anti-clockwise. So the length of the line will shrink by the modulus that you're dividing by. So in this case, it will shrink by 2, enlargement shrinking will be by scale factor 2, if that makes sense. And you'll be rotating clockwise rather than anti-clockwise. Rightio. So that's about it really. There was an activity to do in pairs. It was about sticking some complex numbers on a sheet and labelling them, but unfortunately because of COVID we're not be doing that one. So there is a worksheet for you to do with some questions on that recap a lot of VAS stuff. So as I say, really good revision for your exam that's coming up. So today that will be the end of me, and I will see you next time for probably some more complex numbers online. Right, take care, have a good evening or whatever you're up to, and see you soon.